hopefully you have a week to soak those in. Oh, it's recording now. Great. Okay, cool. Yeah, I also wrote on here, there's only one more quiz after quiz 9. We've almost made it through all of them. So it's exciting. Okay. Anyway, let's go ahead and get to the topic for today. So we're doing 4.8 and 4.9, but first I'm going to do just a quick review of 4.7 just to make sure we got that. Just a couple of basic questions. The one I did at the end of last class probably will not. Here, I'm not going to give you one like that because I think either of these two are going to be more prevalent and more important to work with. So if I have an integral like this, so it goes from 1 to infinity and it's 1 over x squared dx. What should be my first step to evaluate this? What do we think? What do we say? What was the first thing last time? So we want, yeah. So I'm going to replace this infinity with a variable of sorts. It can be whatever you pick. The book generally puts b there, so I'll just keep with that. But I don't simply just replace it. I want to take the limit as it approaches infinity. Okay, so essentially I'm taking that infinity and putting it down as a limit. So it's a little bit more, I guess, what we're used to, a little bit more formal. Okay, so from here, right, aside from the limit, this is a problem I know how to do, right? How do I integrate 1 over x squared dx? So we're going to take the antiderivative, right? So what's my first step to take the antiderivative of this?
X squared to the top.
The limit as the b approaches infinity of integral from 1b of x to the negative second power dx. Okay, now what do I do? Yes, yeah. This was actually a part of one of the questions in the test, so hopefully you guys knew how to do this one. So what's the integral? What's the integral? What's the antiderivative? It's going to look like. It's going to turn to 1 over x, but it's also going to carry a negative sign, right? Because it turns into, so we have the limit as b approaches infinity of x to the negative 1 over negative 1 evaluated from 1 to b, right? Which is the same thing as the limit as b approaches infinity of negative 1 over x, and then that evaluated from 1 to b. Okay, so I'll just continue over here. If I take the limit, let's see, limit as b approaches infinity. Now what do I do with these two numbers? What do I do with b and what do I do with 1? Plug them in, okay? So what do I get when I plug b into and b in here?
Negative 1 over b.
Good. Okay. What do I get when I put 1 in there?
Negative.
Yeah, just negative 1. And then what do I do with them?
Subtract them.
Subtract. So I have negative 1 over b minus negative 1. Okay. So minus negative 1 is just going to turn into a plus 1, right? What is the limit as b approaches infinity of negative 1 over b? It's 0, right? Because 1 over something huge just goes to 0, right? So then I just end up with 1 out of that. Because this piece goes to 0, so I'm left with this plus 1. Okay? Does that make sense? Is that good? Okay, again, this is you might, in another example, you might have to do a little bit of u substitution, maybe to fix it, but it's the same, it's gonna be the same process. Okay, let's try this one. What do I do? What's the problem with this one first? Can't plug 0 in right now, good. So how should I rewrite this? What should I do with it?
Split up the range.
Well, we don't necessarily have to do that in this case, right? And the other one, we have to do that because it was in the middle of the range, right? This is only on one end of the range, so if I split up the ranges, I'm gonna have like 0 and then 0 to 1. It's not gonna, it won't really help us, so
Can you
I'm not gonna split up the range.
take the limit of B as it approaches 0 from the right?
Good, because we're going 0 to 1, right? So if I'm looking at that block, then I'm on the right side. I'm coming to 0 from its right side on that block. So I do 0 to the right. And then so the integral from B to 1. Okay, and maybe we'll save some time here. How can I rewrite x to the 3/4 power to integrate it? X to the negative 3/4. Okay. What's the integral of that? Or how do I do it? So we're gonna have the limit as b approaches 0 from the right of x to what power?
1/4.
So the 1/4, because I take negative 3/4 plus 1 over negative 3/4 plus 1, right? And then I evaluate that from b to 1. So we have the limit as b approaches 0 from the right side of x to the 1/4 over 1/4 from b to 1. Okay. Which, just a quick rewrite, if I have 1/4, what can I do with that? Good. So it's just, it turns into, so when b approaches 0 from the right of 4 times x to the 1/4 power from b to 1, because the 1/4 multiplied by the root. Okay. Okay, so now, so the limit as b approaches 0 from the right of, okay, what do I get when I plug 1 in there? Well, it's 4 times 1. It's 4, right? Right, 4 times 1 to the 1/4. So it'd be 4. Okay, what do I get when I plug b in there?
4 times B to the 1/4.
Exactly. Where I'm just putting b in, right? So it's just 4 times b to the 1/4. Since I don't know what b is, I can't really do anything right now. So I have 4 minus 4b to the 1/4. Okay. So can I take the limit now? Okay, good. What is the limit as b approaches 0 from the right of 4 times b to the 1/4? 0. So what's left? 4. 4 minus 0, which is 4. Okay. So the only thing that's different in these problems is that you have a limit that that's a part of it, but otherwise you're just integrating it. Okay. Good. Any questions on that? Is that a good? Just a quick recap on that to make sure we get the basic idea. Good. Okay. Great. Need some more excitement. Need some more excitement here today. You guys want to hear a joke?
Sure.
Sure. Okay. So the joke goes is that the worst place you can be when you're taking a math test is between 2 identical twins, especially a calculus test, because there's no way to differentiate between them. Okay. Let's see. 4.8. Okay. Let me open up here. Okay, so 4.8 is called the constant of integration. So what we mean what we're talking about, right, again, is if I'm taking, if I do the integral 2x dx, the indefinite integral, then I just simply get x squared, but I have to add a plus c on there, right? So in this case, we're very interested in focusing on this plus c term, right? Because, right, there's going to be real world problems where I don't want to have, and I'm not going to have an infinite number of options of functions to choose that have this rate. I need a particular circumstance, and so that's going to guide my C, right? And the book kind of just stresses again, like, what we're seeing. And so if I take x squared, right? So I take all these different x squared plus c's and kind of put them on this graph, right? What's going to happen is that at any particular point, so let's say at this point, the derivative of all of them is going to be the same value, right? That is that the slope of each of those lines is going to be the same thing, right? So I can at least get the shape of the curve. They're all going to be the same in a general sense, but I need to know exactly where I hit at, right? But the nice thing is that this is where the idea of so to be able to know where we're going to hit at, this is where the idea of like an initial, sort of an initial condition comes in. Right. So to demonstrate real quick what I'm talking about, the book has a problem that says find the function where whatever dx is equal to 2x, right? So where the derivative is 2x, and the graph passes through point 2,5. Okay, so this is an example problem to kind of help us understand how we can get our C's in kind of the situations where we would have them, right? So the first question, right, the first part of this question is find the function where the derivative is 2x. So what is the function where the derivative is 2x? It's already up on the board, right? It's x squared. So y has to be some form of x squared plus c, right? That just comes from integrating that. Y has to be some sort of x squared plus c, right? But we're given an extra condition which says that it needs to pass through this particular point, the point being 2,5. So what's going to happen is, right, 2 is an x or y value, x, and 5 is my y value, right? So if it passes through this point, this graph does, then I should be able to plug 5 in for y and plug 2 in for x, and I should be able to get a true statement out of it, right? So if it passes through 2,5, I need this equation to be true whenever I put 5 into it, right? So we have 5 is equal to 2 squared plus c. Any guesses on what that c is?
1.
C is going to be 1. Because we have 2 squared, which is 4, and we need 4 plus 1 to give us 5, right? So the particular function which satisfies this, so the answer in this case basically would be x squared plus 1, right? So we had an infinite number of options to choose from initially, but because I wanted to pass through this particular point, I got this answer. Okay, so let's take this concept and further. Okay, we had talked about when we first mentioned antiderivatives, kind of bringing back our topics about velocity and acceleration. Right, and the discussion we had there was that if I wanted to figure out what the velocity was, right, I just could take the antiderivative of the acceleration and that would give me the velocity, right? but the issue at that time was, well, I don't know what the constant is, right? So the velocity could be an infinite number of possibilities, right? So, like, it was just, it was a problem that didn't make a lot of sense at the time. But now with this in mind, and now that we're going to be given some, like maybe a starting point, right? Maybe that when your time is 0, you're given some particular velocity. And when you start, you might be at this particular position. That really helps you to guide the curves, and really it helps you to build the system adequately so you can see what's going on, right? And the book goes so as far as to kind of put it in terms of what we're familiar with, right? If I want to find, so generally we're given the acceleration, right? We'd start with an acceleration. We're kind of starting from the bottom and working up. If I want to get the velocity, I simply just take the integral of the acceleration, and this gives me the velocity equation, right? And then if I want to get the velocity equation, or if I want to get the position equation, I simply just take the integral of the velocity, right? Which makes sense. Remember, I mean, again, if I wanted to get the velocity, I would take the derivative of the position. If I wanted to get the acceleration, it would be the derivative of the velocity. So now I'm just working back up, right? And so these are the equations we're going to be using in a lot of these problems. Okay, so let's go ahead and take an example problem. Okay. Trying to see if it okay. It's I think the book just lays out some basic assumptions that you have. Kind of saying if we're on, right, a lot of times I would say like when it hits the ground, when it's on the ground, that just means you're starting at 0. And then it begins at t equals 0. You're not going to be good before that, but if we need to talk about that, we can. Let's go ahead and move on to an example problem though, so we can see what sort of applications we have with this. So I'm gonna round just out of the book. So an object. So an object is hurled upward. On the ground. At a velocity of 25%. Okay, and the question, there's 2 questions, which is how long does it stay in the air? And the second question is going to be, how high does it rise? Okay, so I'll write the question there. We'll probably need to move back to this side to be able to work with it. Okay, so the first question, how long is the object in the air for? Okay, so in order to be able to answer this question, right, we need to, if we want to know how long it's in the air for, right, it leaves the ground at the start, right? So it's only going to be as in the air as long, right? So maybe we'll draw a picture, right? Let's say the object is thrown up like this, right? If we want to know how long the object was in the air, then we need to really see what time this is, right? What t is at this point, because that's the end point, right? So everywhere between that, I was up in the air. So we need to, right, in order to figure out that time, right, that's a position thing. To figure out where I hit the ground, it's a position. So I need my position function. But right now, the only assumption that I have is that my acceleration, which sometimes it gives it as like 9.8, but the book, to make your life easier, is going to give it as -10. second squared. So we're working on Earth. We're assuming everything's happening on Earth right now. Is the acceleration is negative 10 meters per second squared, or approximately that, right? That's kind of the acceleration of gravity on us, right? And that affects everything when we throw it in the air. So if I want to find, I need to get to the position, right? So to get to the position, I have to go through a couple of integrals, right? I only have the acceleration, so first I need to get to the velocity. So how do I get the velocity from here? Take the integral, right? So I'm going to take the integral of A. So it's the integral of negative 10. What's the integral of negative 10 dt? Yeah, and in this case, it'd be negative 10 t,
Yeah.
not x. And then we have a plus c term. Okay, so this is my velocity. Okay, now the question is to figure out, okay, well, you know, I can't just keep these c's kind of random. I started with something, so I need to figure out what c is going to be, right? Do we know anything about velocity in this problem? It started at 25 meters per second. When we say we started, what time is that? Time 0. Okay. So this 25 in conjunction, it starts at a velocity of 25 meters per second, means that whenever we're at time 0, so this is for the velocity here. Whenever I'm at time 0, my velocity should be 25. Right? So that should carry over here, and so that means that V, so again, I'll write that point over here for the velocity. So when I'm at time 0, I should have a velocity of 25. So that means that when V is 25, then I should have negative 10 times 0 plus a constant. Right? So what's that constant? It's 25. If you have negative 10 times 0, it's just 0. So we get, so this gives us that C is equal to 25. So from that point on, from there, we get that V is equal to 25 minus 10t, or you could write negative 10t plus 25. It's the same thing, right? Addition is, you can switch around. It's the same idea. But if it's easier to see, I'll write it as well. If you like negative 10t plus 25 instead. Okay, so that's our velocity. Okay, based on the information given in the problem. Okay, so that's my velocity. How do I figure out my position? I'm going to take the integral of this again. Right? So I'm going to take the integral b dt, which is the integral of 25 minus 10t dt. What's the integral of 25? 25t. What's the integral of negative 10t? So we end up getting negative 5t squared, right? Because it's t squared over 2, and the 2, so the 2 divides the 10, and we just get negative 5t squared. Okay, is that it? The velocity. Yep. Which, if it's helpful, maybe we can call this C1 and call this C2. Okay, so this constant is actually easier to find, right? Because so we're talking about position right now, right? So this is my S. What do we know about position? Starts at 0. At time 0, we started at 0. We're starting at the ground, right? So I have the point 0, 0. Whenever I'm at time 0, my position 0. Again, maybe to reiterate, when I'm at time 0, my velocity is 25. Okay. So if I plug that in, this is saying that S equals 0, which is 25 times 0 minus 5 times 0 squared plus C2. So what's C2? It's 0. It has to be. These both turn to 0, so you have 0 equals C2. So C2 equals 0. Okay, so let me make room, and we'll write out these functions that we sent, right? So again, let's restate.
What's our velocity? 25 minus 10t. I want the whole function, right? Not just at the beginning. And then what is the position? Position function. (25t minus 5t squared). Okay, so just based on the information I was given the problem, I could reconstruct the velocity and the position from knowing the acceleration. Okay, questions so far on this? Okay, it's really just taking points that you know and plugging them in. This is kind of what the initial condition stuff is about. I'm saying whenever I start at 0, I am at a velocity of 25. And whenever I'm at 0, I have a position of 0. And so I can plug those into the respective functions to be able to get where that c is, just like with the x squared plus c example. Okay, so now we want to be able to answer the question, right? We want to say how long is the object in the air? So again, we are wanting to find whenever it hits the ground again, right? This point here is when t equals 0. So I want to be able to find what this time is. How do I do that? Yeah, so I'm gonna set s. So we'll take that 25t minus 5t squared, and I'm gonna set that equal to 0 because that's my position. So I want to see when the position is 0. It's clearly going to be at 0, but I want to see the other one. I want to see when else it's going to be at 0. Okay, what do I do next? Pull out 5t. If I pull it out of 5t, what's left? 5 minus t. Okay. So t, we either have t equals 0 or t equals what's 5? So I set 5 minus t equals 0. 5. Okay. So how long is the object in the air? 5 seconds. Okay. How high does it rise? So we're kind of going back to max to the min, right? So let's kind of recall back from, actually that was like 2.6, but obviously every 3.1, 3.2 helps. So if I have my position function and I want to know when it hits a maximum, I need to know when its derivative is equal to 0, right? What is the derivative of the position in this case? What is it? Okay, that's fine. I understand. I'm trying to build. So if we had, right, so again, let's say I have a random function. I need to move this. Let's say I have a random function, x cubed minus 5x squared, and I want to figure out where this hits, where this is maximum and minimum. How do I do that? You take the derivative of it, right? So, and then the derivative would give us its critical points, right? So if I'm talking about, I wanted to talk about how high does it rise? Does it rise, right? So I'm focusing on the position. I want to see when the position's at its highest, right? So if I want to know when the position's at its maximum or minimum, what do? You take the derivative of it, which is what? It's the velocity, which we already have that, okay? So in other words, if I'm thinking how high does it rise, I need to see when the velocity is equal to 0, right? Because that's going to be when it hits that high point, right? So at this point, you want your v to be 0, okay? And at least in this example. So I'm going to take 25 minus 10t and set it equal to 0. Okay. So we solved that. Yeah, so we can, this is just a linear equation, so I can add 10t to both sides. So we have 10t equals 25. So what's t? T is not 2, right? 2 times 10 is only 20. 2.5. or you can write that as 5/2. It's the same thing. Okay, so that's the time when it gets to the highest, right? That's not, or keep in mind, that's not what our question is asking. Again, I want to reiterate, please read what the question is asking. It asks how high, not when, right? If we're asking when, we want time. If I'm asking how high, I want position. Okay, so we have the time. How do I figure out the how high part? To what? Not to the B equation, to the S equation. Good. So we want to take that and plug it back into S up here.
So let's see if they do that here. I'll
Save some time. So the position for B is going to be then 25 times 2.5 minus 5 times 2.5 squared, which ends up being 31.25. So that is the highest that it goes. Okay, so again, this in a way, this is using, this is problems that you've already done, but now instead of starting from the top and working towards the bottom, sometimes you have to start from the bottom and work towards the top. Right? You may only know the acceleration, you may not be given the position. And this is probably actually more normal than the other cases. Because we don't typically know position, we want to start with acceleration and build up. We always know gravity. That's great. Gravity doesn't change. That's good. That would be good. That would be good. Okay. Any questions on this? Does this make sense? Are you at least a little bit, obviously you have time to look over and understand it, but you at least a little bit comfortable with the ideas here? Okay.
So let's see. They have a couple more problems. Well,
Room. Maybe we'll do another example of that real quick. Okay, so next thing. Is we'll do another one of these velocity sort of problems.
we said we have that an object is hurled, so maybe I won't write up this one.
But here's another example. I'll kind of draw a diagram of this one. Then we have so imagine there's a building and I am hurling down. So I'm hurling something down, an object, from the top of this building, which is 20 meters high. And I throw it down. So here's me. Let's take figure. Some arms. Throws the object down at 5 meters per second. So that's the velocity he's throwing down, right? So then we ask, find the time it takes to reach the ground. Okay. So I want to find how long it takes until it gets here. T equals what when it hits the ground. When I throw it. Okay. So again, we're not given a position function, we're not given a velocity function. We're going to need those. But for now, we don't have that. We have some numbers, but we don't have anywhere to put them yet. But one thing we do know is that the acceleration is going to be negative 10 meters per second squared. Again, that's gravity, right? We're still on Earth. Gravity still applies. If I give you a problem, I'll be sure to include that, just to make sure this is the gravity we're using. If I decide to put it on the balloon, I can do that too. But negative 10 is usually a pretty nice number to use. Okay, now, so I know the acceleration, right? If I know the acceleration, can I get the velocity? Okay. So I take the integral, right? Negative 10 dt. What? Negative 10 c plus c. Right? So this is my velocity, right? What is my initial velocity? So yeah, in this case, maybe I'll kind of put this straight down so we can get the picture a little better. It's -5, okay? Because I'm not shooting it upwards now, I'm throwing it downwards, okay? So my initial velocity, so we basically have the initial point 0 to -5. In other words, we want v of 0 to be 5, right? Just as v as a function, okay? So v of 0 should be -5. Which is -10 times 0 plus C1. Good. Yeah, so this becomes 0, and so we're left with that C1 is -5. So V is going to be -10 T minus 5. Okay, make sense? Great. Okay. Next, we're gonna take, right? We want to. The question is asking when it hits the ground. So for that, I need to know the position, right? When it hits the ground, I need to know when it's at that position 0. So I need to get the position. Can I get the position from here?
Yeah.
How? Good. So which is the integral of -10 t minus 5. -5 t squared minus 5 t plus some c2. Okay. Now, so this is my position, right? What do I do now? Is there anything I know about the position?
Send it to 0.
Says we need to find C first, right? We don't know C. So yes, we know that we start at 20, right? So our position now is 20, right? That's where we're starting at. So when we're at time 0, my position is 20, right? So maybe I'll make some room here. This. Okay, so when I'm at time 0, my position needs to be at 20, right? Because we're saying ground level is 0, so I'm 20 meters above that. Okay. So I plug that 20 into where? Well, yeah, we plug it's going in for S, right? So S is 20 in this case. And then where do I plug the 0 into? All the time, right? So I get -5 times 0 squared minus 5 times 0 plus C. Okay, so what's my constant? 20. You might be picking up by now, but generally, right, you're given your starting conditions, right? And if you're given your starting conditions, then whatever that number is you're given basically just becomes whatever the constant is, right? Because we said velocity initially was -5. Well, C1 was -5. We said position initially was 20. Well, C2 became 20, right? That is just what those initial values are. You can always go through and do it this way, but if your mind's at a point where you're like, oh, well, I don't need to do all the hard work, let me just slop it in there because I know that. You can. Now, sometimes you might be given that at time 1 second, you might be at position 30 or 15 or something. So you might be cautious there. But if that's at 0, it should be pretty easy to work through. Okay, so once we know C2 is 20, that gives us that S is going to be 1. What's that S function look like? plus 20, right? Good, okay. So this is our position function, right? But I need to figure out when it hits the ground. How do I figure it out? Yep, I take this and I set equal to 0. Okay. So how do I solve that? Okay, they all have a 5 in common. That's good. I might even say take out a -5, just because that makes my life a little easier. So I'm left with t squared. What's my left with? Plus t. Okay. Let's see. We're at, it looks like, yeah, so this actually does not, you can try to factor this if you want, but there's no factor that makes this work. There's actually just like the numbers that they give are not nice. So obviously -5 can be 0. And so you would take this and put it into the quadratic formula, which I know a lot of you know, I saw it. So, and when we do that, where you get t is going to be, let's see, is it -1 plus or minus the square root of 17. Okay, here's the question. Do I include both of those? Why not? Right, so they both do exist, but one of them is negative. So you're going back in time, which we're not gonna have. It's basically saying that it's, if you assume there's negative times, basically you're saying that the ball was able to like, just kind of came through the building. So that doesn't, right, so we don't need to include the negative one. We just need the positive. So then this would be right. Okay. Does that make sense? Maybe, okay, good. Awesome. So the last thing I would say is I would maybe just because I want to kind of just real quick cover the last section, but maybe look over, you can look over examples 5 and 6 in the book. Those are helpful. 5 is just another example of what we've already done, same thing. 6 just takes it, and instead of doing it for velocity acceleration, it applies it to. Okay, so this section was really all about this application. Okay, good. Any last questions here before I clear off the board? Yeah.
What is the negative value you were talking about? You're talking about the plus or minus squares?
Yeah, so normally when you solve this, right, you get plus or minus square root of 17 over 2. But if you let root 17 be minus, the time is negative. Well, we don't allow that, right? We're working with real world situations. You don't allow negative time. So I don't need to include that one. All I care about is the positive.
Thanks.
Okay. So for the last section of chapter 4, that you'll be learning for the test. I know many of you really liked doing the rectangle approximations. So I'm going to give you 2 more methods to do that. I promise that, you know, it's the same thing though. If you know how to do the rectangles, you can do these ones as well, because it's the same process to plug in. Okay, so let's write here 4.9. So there's 2 rules that we're going to learn here. I'll do one on this side and one on that side. Fair? Great. Okay. First. Trapezoidal rule. Okay, so what do we mean when we say trapezoidal rule? So if I have a curve like this, right, and I want to find the area underneath it. Now I know we have integrals now, but there's going to be a lot of them we still don't really know how to evaluate. And so we still need to know these approximation methods, which is why we're I'm teaching this. So don't think this is pointless now. I have all my nice methods. They won't always work. Okay, I know for sure because we haven't even We haven't even touched anything with trig functions or with the log or exponential. That's come too. But whenever we were doing rectangles, right? At times, the best we could do was like, just. I mean, this one doesn't end up looking too bad, but it would be a lot more helpful. We could probably get a better area even if I could, instead of having to take all of that. Instead of taking all that extra area, right, that's missed or taken with the rectangles, if I just kind of cut that piece off. And here, I take it and again, kind of cut off that top half. That one's fine, we can kind of leave that one. But again, cut that one. This, that, this, that, this, that, right? It looks a lot better, right? Now the shapes, we're still not using like curved shapes in this necessarily. These are straight edges, but we're using trapezoids, right? Which remember, in general, a trapezoid, right, would look something like this. More specifically though, in our case, we want our trapezoids to be more of this form, to where I can kind of take them and make them as small as I want, and then kind of bend the edges up that's necessary to get as close to the curve as possible. So this is the trapezoidal rule comes in because it shaves off a lot of what we lose from the rectangular, doing a rectangular approximation. Now, the nice thing again about trapezoidal rule is that it's going to use, right, again, we're going to be pulling back our same definition. So I have delta x is b minus a over n, and we have xi is I of x. I'm going to be using these same two terms to be able to figure out what this is, right? But now our formula is going to get a little more interesting. Okay, so so we can figure this out together, right? Who can recall? So let's say that the length of the bottom is, I'll call the length of the bottom L1, I'll call the length of the top L2. And then let's say that the trapezoid has some certain height attached to it. Who remembers what the area of a trapezoid is? Okay, so to find the area of a trapezoid, all that needs to happen is first I start off and I say I have 1/2. And then I take the sum of the top length and the bottom length. Right, so I sum L1 with L2, and then essentially I divide it by 2. Right, so it kind of averages it, makes it more like a rectangle. So then once I have that, I multiply by the height, and that gives me the area of that trapezoid. Okay, so this was the area of a trapezoid. That's how we found it. So how this applies over here, right, is again, I have all of these various trapezoids, right? Now, in this case, we were kind of looking at it as here's the top, here's the bottom, and then the height's in the middle. But for each of these, I'm going to kind of think about them sideways, if that makes sense. So they're each going to have a certain height attached to them, which we want to make that consistent. Just like with the rectangles, we'll call that height delta x. Okay, delta x all the way through. So let's think about, so in this case, we're going to have, so xo, x1, x2, x3, all the way up to xn are going to be our terms, right? So if I want to get the area of this trapezoid, just this one as an example, right? Again, this is our function. So the length of this side is going to be just the function value at xo, right? So let's say I want the area of this particular trapezoid. So the area is going to be 1/2, right? Again, pulling it 1/2 from here. F of xo, right? So I take the function value at whatever xo is at that point, and I add f of x1 to it, right? Consider this L1, consider this L2. I take the average, that gives me kind of the length that I need. And then I multiply that by the height, which is delta x. So this is call this A1. A2 is going to be 1/2, right? So I do the 1/2 again, but now I move to the next one, right? So the length of this side is f of x1 plus, what's the length of this side going to be? F of x2. Times delta x. Right? And then I keep on going, right? Until I get to xn, right? So the last, basically the last area I'm gonna have, maybe I'll use words for a long time, maybe I'll cover this in the next class. You would get until an, right? You would keep going, and then this would be 1/2 times f of xn minus 1, right? Plus f of xn delta x. Okay. So then, of course, if I want to get the area of the whole section, I add up everything together, right? I add up A1, A2, all the way up to AN, right? So what do all of them have in common? They have a delta x and a 1/2. So when I add up the area, since they all have a 1/2 and a delta x in it, I'm gonna take that and I'm gonna put it on the outside. Okay, I know those are in all of them, so I don't need to add them to each term. I'll just keep it separate. Okay. Now let's just consider when I add A1 and A2 together, right? So again, the 1/2 and the delta x don't matter here. We're just concerned about what's happening on the inside. When I add those together, how many fx1s am I going to have? You know, 2 of them, right? How many fxo's am I going to have? You're just going to get 1, right? Now we didn't write it, but A3 would have f of x2 plus f of x3. So how many f of x2's would I have? F of x3 would have 2, x of x4 would have 2. All the way up to f of xn minus 1, I'm going to add 2 of those. But then f of xn is by itself because I only add it one time. So what happens is for trapezoidal rule, I get 1/2 delta x times f of x0 plus 2 times f of x1 plus 2 times f of x2 plus all the way up to 2 times f of xn minus 1 plus f of xn. And this is our trapezoidal rule. Approximation. Okay, so looks big. The gist is that the ways of this is different than the rectangular, right? Your delta x is now half of your delta x. And then each of your terms, you need to include an f of xo as well, so because I need to include the left side now. But each of the terms in the middle is multiplied by 2. The 2 ones at the end are just themselves, but everything in the middle needs to be multiplied by 2. So all in all, this ends up being my trapezoidal. Okay, so I couldn't get the Simpsons rule, that's okay. We'll do that as we get in next class, as well as the review time. Oh, no. Yeah. Okay, wait, we'll stick around for that. Yeah. Can I do the bonus question? Or would you rather me do something similar to the bonus?
Oh, I just didn't know.
I guess, yeah, maybe I won't. Sorry, if I'm not seeing online. This time. Okay. So something akin to bonus question. Okay. X squared over the square root of 1 minus x squared, I want to take the integral with this respect. Yes, actually. I'll do X. This will be good. Okay. So how do I evaluate this integral? Okay. What ideas do you have?
Starting with the method, but it's not gonna work
How do you know that?
because I worked through my du and I did that x. That's,
You actually make a good point though. I should probably make that X. The one on the quiz was good. I'm gonna make that X cube.
so if I take my u as 1 minus x squared, or x, 1 minus x squared, my expected du is gonna be is, 1/2
Negative 2x, right?
negative.
In this case. Yeah. Right, so you would divide -2 from both sides. And we would be left with x dx.
So you're missing another x squared, so it'd be your d would be x squared. D over 2.
So you're saying your predicament right now is we have x squared or x cubed. Well, actually, one of the x's gets taken. X squared over the square root of u times du. Okay, well, I understand the predicament. If only there was a way we could write x squared times du.
Yeah, we
Aha.
did that exactly.
U equals 1 minus x squared, so x squared is 1 minus u. Okay, a little tricky, a little bit so we have the integral of 1 minus u over, because x squared, so for yours as well, since u is 1 minus x squared, since I had this little x squared term that was still in here, I just simply said let x squared, I'm going to rewrite x squared in terms of u, and I'll replace that instead, because I want everything to be in terms of u, and I'm good, right? And it still works because I still sucked up the derivative pieces I needed to, but I just had to do an extra little piece. So I have 1 minus u over the square root of u, du, and then -1/2. Okay, now what do I do with this?
Plug u back.
Not yet. If we plug u back in, we'd get back to the original problem.
Oh,
So we don't want to do that.
bring it up to the top.
So we're gonna multiply it, right? So, or I can just say that square root of u is gonna divide from each thing, right? So we have 1 over the square root of u,
Oh, okay.
which is u to the -1/2 power. Right. And then u divided by the square root of u, which is the square root of u, or it's u to the also the power of u. Okay, so again, I can just rewrite that square root of u as u to the 1/2. And then I kind of had it written on the board. You remember I had x to the n over x to the m equals x to the n minus m, right? Feel free to use that here, or even 1 over x to the m equals x to the n. That's kind of why I gave the hint for 3, because that was the idea for 3, but it turns into this. Okay, can I integrate that now? Okay, what is that going to integrate into?
2 square root of u.
Yeah, so here it's going to turn into u to the 1/2 over 1/2. What does this one turn into?
U to the 3/2 over 2.
And then you'll have a plus c on the end. So now I'm going to work a little bit of magic to try to simplify it. So these 1/2 cancel out here, and actually I could get rid of this 2 as well, ends up going away. So that's a little bit of algebra. If you have any questions in particular on that, you can ask me, but I'll probably skip it for now. minus, or so plus, minus over 3. C, so we get that, and then you just plug u back in. So we get negative 1 minus x squared to the 1/2 plus 1 minus x squared halves over 3.
There was a point where it's staring at that for a minute, and then I thought, it popped in my head to try using the complement of 1 minus x squared square root, and I thought I was onto something. Another, I'm even in the ballpark.
Yeah, it's just, you just have to be wary of like, I can move that stuff around if I need to, so.
You guys have any questions for me?
Practice some integration. Trapezoid rule at least then. Thank you for watching online if you're here.